Hello, welcome to the course PH5 BO6 Electrodynamics 2. The contents of this course is taken from Introduction to Electrodynamics by David J. Griffiths. In today's class, we will continue to discuss topics from Chapter 7 Electrodynamics. In the last lecture, we discussed a seminal result in electromagnetism known as Faraday's electromagnetic induction law, which says a changing magnetic field induces an electric field. So whenever the magnetic flux through a loop changes, electromotive force E equal to minus d phi by dt will appear in the loop, where phi is the flux associated with the loop. In other words, EMF is the negative rate of change of flux. This is known as the Flux Law. The question is, what is the direction of this induced field? So this is given by famous Lenz's law. It says the induced current will flow in such a direction that the flux it produces tends to cancel the original change in flux. So if you have an increasing flux, the resultant field will try to decrease the flux. On the other hand, if you have a decreasing magnetic flux, the resultant field will try to increase the flux. Now this can be demonstrated using the famous jumping ring experiment. Imagine you have a solenoid, pass current through it, there is a magnetic field developed along the axis. Now if you want to concentrate the field, you can place a conducting core inside the solenoid. Now you place a conducting ring on top of the solenoid. If there is no current, the ring stays as it is. When current flows through the solenoid, you will notice that the ring is jumping upward. Now this is an outcome of electromagnetic induction. So using whatever induction theory we have learned so far, let's try to analyze this. Originally, there is no current, there is no field, so flux through the ring is zero. When current starts flowing through the solenoid, a magnetic field is developing. Consequently, the flux through the ring is increasing. So you have a changing magnetic flux which induces an electric field. And what is the direction of the electric field? It is in such a direction that it opposes the original change in flux. Now the original flux was created by a current flowing in this direction. So consequently, the induced field will drive current in the opposite direction. So I have current flowing this direction here, current flowing in this direction here. Since opposite currents repel, the ring jumps up. Now let's do a quick problem which will make concept clear to you. A uniform magnetic field B of T pointing straight up fills the shaded circular region in this figure. If B is changing with the time, what is the induced electric field generated? First, let's get the directions right. If you recollect the case of current carrying wire, assume that this is a straight current carrying wire. Current is flowing in the upward direction. So this is the direction of the electric field. And the magnetic field was in the circumferential direction around the current carrying wire. Now here we have the converse case. Magnetic field is in the vertical direction. Consequently, the electric field is along the circumferential direction. Now assume an Amperian loop of radius S. The magnetic field changes with time. So the flux through the loop changes. This induces an electric field along this loop. Now if you take the closed line integral of the electric field along this loop, you can write integral E dot dl. Since electric field is uniform along the loop, you can take electric field outside the integral, and line integral along this path gives you the circumference 2 pi s. So line integral equal to E into 2 pi s. Now from the flux rule, Integral E dot dl is the induced EMF, which is equal to negative rate of change of the flux minus d phi by dt. Flux you can write as product of square area of the loop pi s square multiplied by magnetic strength B of t. So when you take derivative of this, you get minus pi s square dB by dt. Now the direction is circumferential, which is indicated by the azimuthal angle phi cap. So if B is increasing, the electric field is along the clockwise direction. On the other hand, if the strength of magnetic field is decreasing, then electric field will be along the counterclockwise direction. Now imagine that you have two conducting loops, loop 1 and loop 2, which are at rest, and current I1 flows through loop 1. So this produces a magnetic field B1, and the magnitude of the magnetic field due to a small length segment dl1 of loop 1 at a distance r can be found out using the Biot-Savart law as B1 equal to mu naught by 4 pi I1 integral dl1 cross r cap by r square. If you notice here, B1 is proportional to current flowing through the loop 1, which is I1. Some of these magnetic field lines passes through loop 2 also, so this produces a magnetic flux phi 2, which can be written as integral B1 dot dA2, where dA2 is the area element associated with loop 2. Since B1 is proportional to I1, phi 2 is also proportional to I1, you can replace the proportionality with a constant M21, which is known as mutual inductance of these two loops. Now, you can always write magnetic field in terms of magnetic vector potential. So phi 2, which is written as integral B1 dot dA2, now can be represented as integral curl of A1 dot dA2. This is an area integral which I can convert into line integral using Stokes theorem as closed integral A1 dot dL2. Now from the definition of magnetic field, I can rewrite the definition of the magnetic potential as A1 equal to mu naught I1 over 4 pi integral dL1 by R. This is using the Biot-Savart law. Now if you substitute for A1 in this equation, you can write phi 2 equal to mu naught I1 over 4 pi double integral dL1 dot dL2 by R. If you compare this equation with this equation, this term is the mutual inductance. So I can write M21 equal to mu naught over 4 pi double integral dL1 dot dL2 by R. This is known as Newman formula. Now there are two important observations here. First one, this term mutual inductance is a purely geometrical quantity. It depends on the sizes, shapes and relative positions of the two loops. It doesn't depend on the current flowing through the loop. Second one, imagine that you are interchanging the loops. So in place of loop 2 I have loop 1, in place of loop 1 I have loop 2, and current flows through loop 2. Now we can do the same procedure here, and you can calculate the flux through loop 1 because of the current flowing through loop 2, and the corresponding mutual inductance you can write as M12. So this will be mu naught over 4 pi, and you need to interchange these two integrals, and as you know, interchanging integrals doesn't change the value. And this inside terms, instead of dl1 dot dl2, now you have dl2 dot dl1. As you know, dot product is commutative, so changing the order of the term do not change the value. So in other words, M12 will be exactly same as M21. So flux through loop 2 when current flows through loop 1 is exactly same as flux through loop 1 and the same current flows through loop 2. So the subscript is no more important here. You might as well get rid of that and just write M. So now onwards we are going to represent mutual inductance as M. Now what happens if current through loop 1 changes? So when current changes, B1 is going to change. Consequently, flux through loop 2 changes. So changing flux induces an electric field and EMF in loop 2. You can call that EMF as E2, and from Flux law this is equal to minus d phi 2 by dt. Since phi 2 equal to m into I1, I can write E2 equal to minus m into di1 by dt. So this is the case when current flowing through a loop changes, what happens to its neighboring loop. Now let's try to understand when current flows through a loop changes, what happens to the loop itself. Because we know when current changes, the magnetic field associated with that loop changes. When magnetic field changes, the flux changes. Whenever there is a change in flux, it induces an electric field, which means when current through a source loop changes, it in turn induces an electromotive force in the loop, and this phenomenon is known as self-induction. So we can write flux through the source loop is proportional to current flowing through loop I, and replace the proportionality with a constant L and write phi equal to L into I, where L is self-inductance. And if you follow the flux rule, you can write the EMF associated with the loop is E equal to minus L into di by dt. The unit of self-inductance is Henry. 1 Henry is 1 volt second per ampere. So self-induction is the phenomena in which an electromotive force is generated in a loop whenever current flowing through the loop changes. On the other hand, in mutual induction, an electromotive force is generated in a loop whenever current flowing through its neighboring loop changes. According to Lenz's law, EMF is in such a direction as to oppose any change in current, meaning if you try to increase current in a circuit, then the resultant EMF will try to decrease the current. Similarly, if you try to decrease current in a circuit, the resulting EMF will try to increase the current. So whenever you try to alter current in a circuit, you need to fight against the EMF. That's why the induced EMF is also known as a back EMF. You will find the manifestation of back EMF whenever you work with electrical circuit. One of the common examples is, suppose you have an electrical instrument plugged to the power supply. If you remove the plug while the switch is on, you will find that there are sparks generated in the plug. Now you can understand this in the light of electromagnetic induction. When you remove the plug, you are suddenly decreasing the current to 0. The current changes, which produces an EMF. Remember, this is a back EMF. So you are trying to decrease the current and the back EMF is trying to increase the current. It tries to run the current along the circuit, but now you have an air gap. So back EMF pushes electron into the air gap in an attempt to run the current. So because of this, an electrical discharge happens in the air gap, and that is what you see as the spark inside the plug. So always remember, in any electrical circuit, when you try to change current in the circuit, you need to work against the back EMF. Let's do one quick problem related to mutual induction. A short solenoid of length L and radius A with N1 turns per unit length lies on the axis of a very long solenoid of radius B and N2 turns per unit length. Current I flows through the short solenoid, what is the flux through the long solenoid? Now, from the principles of mutual induction, you know that the flux through the short solenoid when current I flows through the long solenoid is exactly same as flux through the long solenoid when the same current flows through the short solenoid. So for ease of analysis, let's take the reverse problem. I'm going to run current I through the outer solenoid, the long solenoid, and I will calculate what is the flux through the inner solenoid. So this is going to be same as our original problem. Now, when current I flows through the long solenoid, it produces a uniform field along the axis given by mu naught N2 into I. So I can calculate flux through a single loop of the inner solenoid as magnetic field B multiplied by area of one inner loop, which is pi into A square. Instead of B, you can substitute mu naught N2 I. So this is mu naught N2 I pi A square. Since I have N1 number of turns per unit length, the total number of turns is N1 into L. So the total flux through the inner solenoid is phi equal to mu naught pi A square N1 into L into I. So this will be exactly the same flux when you run current I through the inner solenoid, and this flux is going to flow through the outer solenoid. By the way, the mutual induction is going to be mu naught pi A square N1 N2 into L. So that's about the theory of electromagnetic induction. In the next class, we will study what is the energy associated with a magnetic field. Thank you.